Okay, here we are. Um, magnetic dipoles, this is the last part of the chapter that you were doing before the mid-sem, and multiple expansion. Then I'll also today do a little bit of the next chapter, okay, which is going to be through the magnetic dipoles to the magnetic materials. Okay, magnetic materials are nothing in some sense a superposition of many magnetic dipoles. All right, and hence magnetic dipoles is the most important thing to do before I do magnetic materials. All right. Um, so let's say, uh, sorry. So a magnetic field due to a long straight wire carrying current I will. Okay, what is that? Just let me see. Uh, all right. So this is we already know, right? This is we already know, and we know that if I do B dot dl around this, then I'll get mu naught I. Okay, this we are already familiar with. I'm just contrasting it with, so B due to a circular loop of radius r carrying an I on its axis. Okay, so let's reverse the situation. That is, this was a current, and we are looking at the magnetic field, okay, which was in the phi direction. Suppose I have a current circular loop, and then I can look at the on the axis. This we already know, okay. So z axis above the center, you know how to calculate this from dB. I will not go into that, so we know this. All right. So this is something that you have done many times, and this is an important formula for a current ring. Okay, so this is mu naught I by 2 r square. R is the capital R is the radius of this circle. It's not mentioned here. R square plus z square 3 by 2. All right. So if I take, I can rewrite this in a form in which B of z on this axis is I pi r square. I multiply pi and multiply pi here. All right. And multiply a 2 here. So that mu naught by 4 pi I pi r square k. The intention is to, okay, so here also you can see, I'm showing it, that suppose I integrate minus infinity to infinity, bz, okay, it will be, you can think of this minus infinity to infinity is like another huge loop, infinite loop, okay, and that will be equal to mu naught I. I just wanted to contrast you with these two, okay. One is the current, straight current, infinite current, and the magnetic field, and here is a circular loop of current and the magnetic field around the axis, okay. So that is a certain symmetry between the two, and you also will get mu naught I, okay. It's just integral of this from minus infinity to infinity, which is quite easy to do. But my main intention is to show that, in fact, many people take this to a definition. This area of the loop, pi r square into I, okay, is considered the magnetic dipole moment. We'll have more justification for that, but let me motivate by saying this, okay. So m is I pi r square k, and in that sense I can write down for z much larger than r, I can see that because of this, this is goes as z cube. All right, and that is what we expect of a dipole, that for large z, as compared to the radius of the, if it is a small loop, as compared to the field distance, then B of z goes as 1 by z cube, and that's like a dipole. And I define this as magnetic dipole moment. Okay, so this is on the, as I call it, the head-on position. There is 2m by z cube, and that is my sort of motivation of what you are doing. All right, this probably you already know, and so we'll define more
मुझे
rigorously.
क्यों बता रहे हो? हटा दो स्किल को, हटा दो स्किल को, खुल जाएगी वो मोस्ट प्रोबेबली.
Why are you? How come I can hear some other voices? Please don't. This is being recorded as a class almost. All right. Okay. So B of Z. So then you can see it is something like the dipole. And I am motivating the definition of a magnetic dipole as I, of course, it is vector, is a vector quantity, just as P was a vector quantity in electrostatics. Okay. Here it is. There it was the distance between the plus and minus, but here there is no plus and minus. There is no monopole. So there is a current loop is the basic magnetic dipole. Okay. So I pi r square. Of course, we'll do a multiple expansion to do it more rigorously. All right. So yeah, so this Z cube is field dependence is dipole like, and this pi r square is area vector. Okay. If I include this k hat, okay, then it's an area vector. Okay. So let me talk about, since I'm motivating area vector, which is an important quantity then to be understood or to be used for magnetic dipole. All right. So this is easy, but suppose I wanted to a point which is off axis. Okay. Then I cannot use this simple derivation. Okay. So then if I have a formula for calculating B for M for all points, for all field points, then I can also do off axis. All right. So that is the, so area vector is suppose this loop is like that. Okay. Then it's like a proper vector. I can find out an complete area vector for this. Of course, if it is only flat, then there is no problem. Suppose I join from here to here, then the current goes from here to here and to here, and then it's a flat, and then area vector is pointing out only in this direction. All right. But for this part, the current is going like that, and it will be retracing like that, like that. So a combination of this the area vector and this area vector can be considered as the area vector for the even the non-flat. Okay, so it is actually true for area vector can be defined for any loop. All right, and hence since this is going to be an element of my definition for magnetic dipole moment, I would like to concentrate on few results on area vector. Okay, so this is clear. So I first motivate from a very simple demonstration that what we are considering as dipole moment, and then I see that area vector is an important concept that I will require in defining, and it should be like a proper vector for any arbitrary loop. All right, all right. So so any arbitrary loop I can. So if I know the area vector, then if I know the current, the same current, then I can also have the magnetic dipole moment of this non-flat loop. Okay, so that's the idea. So for any arbitrary, I can do that. All right. So let me. All right. So we will look at the area vector for arbitrary loop with right hand sign rule. So when you are saying a vector, we'll always use the right hand sign rule for any area. Okay. So this is about the area vector. All right. So I'll first prove very simple results, which I'll call as lemmas, as mathematicians call it. Okay. That is, there are four lemmas on area vector. For any closed surface, okay, so area vector is for a area, but if it's a closed surface, then the area vector will be 0. Okay, you can see that. Okay, we'll prove it. Okay, but this is a very important result. For a completely closed surface, the area vector would be 0. And two surfaces sharing the same boundary have the same area vector. Okay, if there are two surfaces, if they have if the boundary is the same, then it'll have the same area vector. I'll prove all four of them, but first let's understand what we're trying to prove. Okay, and any area vector, okay, for a curve can be computed in the basis of half r cross dl. Dl is along the path, along the curve, and r is from the origin. Okay, so this also will prove. And an important result which I'll use is, suppose C is a constant vector. Okay, something like, let's say, unit vector. All unit vectors are constant vector. Let's say I cap or K cap. Okay, is a unit vector, and then I take its dot product weights from the R and then go over the loop. Okay, then that is nothing but minus C cross A, or you make it plus by saying A cross C. Okay, but C is a constant vector. So this is an important result that I'm going to use it later. So while solving problems, all these four, especially in answering logical questions also, all these four lemmas could be used. So I'll prove all of them. All right. So let's say an example of an area vector. So find the area vector of a hemispherical bowl of radius r. Okay. So of course that you can say now quite easily, because knowing the lemmas or whatever. So the area vector for the hemispherical bowl will be the same as the area vector for the this. So it should be pi r square k. Okay. If I take the for the hemispherical bowl also, the area vector would be pi r square k, and for this flat also it will be pi r square k. So you can actually show it even rigorously. Okay, so you can take a dA for the hemispherical ball. Okay, for any small area element on the hemispherical ball, and then it is r. R is the radius. So I just integrate from 0 to pi by 2, 0 to 2 pi. Okay, and then you can see that this will not contribute. This will both will contribute 0, because 0 to 2 pi cos phi and sin phi. So only thing that will contribute is cos theta, cos theta d theta, and hence this will become n 0 to pi by 2, and this is pi r square k. All right. So this is just to give an example of, though it's a curved surface, but still I have an idea of an area vector, and area vector is same as the flat circle at the bottom. All right. So by directly from lemma to above also, instead of integration, I could have used this lemma to even also obtain the same thing. Okay. So I'm just doing this to make you familiar with the idea of area vector. All right. So let's go into actual proofs. So before that, let's doesn't sound like so there are two useful corollaries of the gradient theorem. Okay, the fundamental theorem on gradients. I hope now you remember the fundamental theorem gradients. That is the gradient. If you take from a point A to B dot dl, okay, then it is the value of the scalar at the edge. Right, that was our starting point. You remember in chapter 1. So I have now two little corollaries of this, which is useful, which I had tried to use it earlier also. People were saying, how is it true? Okay, but here we would require it. So let me prove it. So let me call it as the fundamental theory, a fundamental theorem of gradient volume. Volume, this corollary 1. There are two corollaries. I'll prove the first corollary. First corollary is that if I take the volume also, this was about line integral. Okay, now this is about a volume integral. Okay, so this should not be a dot. Okay, this is just a del t over the volume, and then it is true of the scalar over the surface area. All right, so this is the fundamental theorem, but this is a corollary of that. Okay, this dot has no meaning. Okay. Okay, the trick is to use, so in proving many of these things, the trick is to use a constant vector C for use of the appropriate divergence of Stokes theorem. Okay, so let me show you that suppose C is a constant vector such that I define, okay, a new vector, the V is equal to Ct. Then if I take divergence of this new defined V, then I can take the divergence of Ct, then that is C dot the gradient of T plus but this is a constant vector, okay, and hence that will become 0, and hence I can say that divergence of v d tau is v dot. I'm just using the divergence theorem, okay. So the only assumption that I've made is c is a constant vector. All right. So then, of course, I can write down that divergence of my, this is V, I've defined as CT, so I replace that, okay, and that is CT, C dot T dA. Now I take my, I use this, right? I use this, and so I can write down this as C dot gradient of T d tau, and I can take this C, this is a constant vector, so I can take this C dot and this, right? Okay, so then I can write down both sides C dot for any constant vector C. Okay, this is true. All right, and hence I can say that if I take the gradient of T over the whole volume, then this is same as these values of C over a closed surface over dA. Okay, so what was the trick? Trick was to define a new vector function, okay, with a constant c, and then invoke divergence theorem to show this. All right, this is the corollary one. I'll call it as fundamental theorem of gradient volume corollary. Okay, so similarly, you can see that the corollary 2 would be a surface corollary. Okay, so fundamental theorem of gradient surface corollary 2. Okay, so this is similar. Okay, so now I take a grad of T cross dA, okay, over surface, and that is, of course, there is a minus sign here, okay, and T over, so this is over surface, and hence it's over boundary. Now it's the boundary over the curve. Okay, so this is gradient, so the appropriate differential is over the surface, okay, over the whole surface, then it is minus of the gradient of TdA. This is the corollary 2. Fundamental theorem gradient, surface corollary 2. Same idea, except that take a constant vector and instead now invoke Stokes theorem. Okay, so del cross V is del cross CT. Okay, I can write down T del cross C, and this of course will be 0, and hence because C is a constant vector, the curl of V is simply minus C of curl of the gradient of T. All right, now one can invoke Stokes theorem because, okay, so Stokes theorem, of course, this is a traditional Stokes theorem, and then I put VCT, okay, and then I use this result almost parallelly, right? Okay, so from here I take it minus C, the curl of gradient of T, okay, integral, so into put into that, and that is C dot, and you can see why am I so of course I'm using this result, okay, the triple product result, and then I can write down this, right? Okay, so and this is just algebra. I've taken out C dot out, and that gives me the result. All right, so okay, so this was minus here. I've just taken the minus on this side and this minus. So in the surface fundamental theory of gradient of surface in corollary 2, the trick is the same. The trick is define a vector function with constant and invoke Stokes theorem. Okay, and that will give you, so you can see that the fundamental theorem of gradient with 2 corollary is actually almost applicable for going from a curve to the edge points, from volume to the surface, and from appropriate differential, of course, okay, from surface to a closed path, line integral. All right, so these are all fundamental theorem of gradients of different avatars of the same fundamental theorem. Okay, so now I'm proving these 2 corollaries because I'll need them in my proving some of the lemmas on the area vectors. Is that clear? All right. Okay, so let's go to the proof of the lemmas. Very simple. Okay, on vector area quickly, one by one. So lemma 1, for a closed surface A is equal to 0. Okay, that's for a closed surface the area vector is a 0. Okay, so I can just invoke the corollary I just proved, that if the gradient of T over a volume is TdA, and then now consider T is equal to 1. Suppose T is a constant. Okay, then what happens? Then volume, so simply, so then T is 1, so dA, and gradient of T is 0. Okay, so A is 0, as mathematicians would like to prove it. Of course, physically, I think you have a feel for it. Take any vector and then go around the whole this thing. Of course, it will come out to be 0. All right. So, but I can use this lemma, the corollary one, and then it is obvious. All right. Now let's go to lemma 2. Two surfaces sharing the same boundary have the same area vector. Okay. Suppose they are not the same. Okay. Suppose there are two surfaces, but their boundary is the same, but the area vector is not the same. Okay. Then what happens? I can always close the surface by mounting an A3. That is, they have the same boundary. Now I put another A3 which will close the surface. Okay. Now the close, and just I proved that for closed surfaces A is 0. So for both of them it will be 0. Okay. Since now both are closed surfaces, by lemma 1 both are 0. So A1 plus A3 is 0, A2 plus A3 is 0, and hence they can't be different. All right. So if the same boundary, then area is the same. And I have just shown you an example of a hemispherical ball and its radius. Okay, as a typical example. Okay. So then what was about lemma 3? Lemma 3 was that A is half of R cross dl. Okay. This is just simply by geometry. I'll just do it by simply. Suppose this is the loop, and I take my another surface which is like that, and then I can consider a little small this thing, this there. Okay, so that is take it out. This is R, this is dl, and this is R plus dl. Okay, now this I can construct a parallelogram, right? Parallelogram area would be R cross dl. Okay, and this would be half of that. So that's that. So dA is half R cross dl, and hence A is equal to integral of R cross dl. All right. Okay. So as simple as that. So you integrate it and invoke lemma 2. So if this is the area of this conical surface, then by lemma 2, the area of this also will be the same as the area of this thing. Okay. And hence the first three lemmas are proven. All right. Okay. So now the lemma 4, which is important for our derivation later. Okay. That is, if I take C dot R, C is a constant vector. Okay. And integrate over a closed path, closed curve, then it is minus the constant vector C cross A. Okay. So that is lemma 4. So then again the old trick, define now a scalar function which is C dot R. All right. So now I'll invoke the fundamental theorem of gradient of surface, corollary 2, okay, which is the gradient of T cross dA. This is already I've proven that, except that I'll now apply it to my new definition of scalar with a constant vector with a position vector R. All right. So now I plug this in. Okay. This is gradient of T, and this is gradient of C dot R. Okay. Then this will be, I just expand it like A dot B. All right. So this will be del cross, we know. This we already know, that del curl of position vector is 0. This is a constant vector, and this is 0. And this is a constant vector of some differentiation, that will be 0. So only term that really survives is constant vector C dot del of R. All right. So now that is equal to, so I am now rewriting this specially in Cartesian coordinate system. All right. So what is C dot del? Cx del by del x, Cy del by del y, Cz del by del z. and R is of course X I hat plus YZ, okay? And so del by del X acting on X of I, okay? So Cx, so that's nothing but only Cx will remain, all right? Cxi. So this will be 1. So for this also this will be 1, and hence this is C. And hence, if I define my scalar function to be a constant vector dot R, then what I've just proven is that its gradient is nothing but the constant vector. Okay, so this is the algebra, but the vector algebra, but this is, okay, now I will use, okay, so I've just shown that the gradient of C dot R, if C is a constant vector, is nothing but the constant vector C. All right. So now I'll invoke the surface corollary 2 that I just proven a few minutes back. And then I say that C cross dA, okay, I can write down this. All right. I'm just invoking that. All right. And now, and hence I can write down C cross dA over the S is this. And obviously that is nothing but this is C cross A. So we have to prove minus C dot R dl. Okay, this is the one. This minus, I'm writing it here. All right. So that is C cross, and this is over the whole surface. This is dA. This is C cross. So it's a little bit of algebra and maths. Okay. But instead of just invoking the result, I thought I'll prove it. Okay. In the book, probably it just invokes that this is true. All right. So remember this lemma. Okay. Understand this lemma. That is, if I take the constant vector and take its dot product with each point in the position, and then integrate over the area, then it is nothing but A cross C. Okay. A is the area vector across the, so I can obtain that. All right. All right, so that is the proven. So I have proven 2 corollaries and 4 lemmas, okay, about the area vector. The corollaries were about the fundamental theorem of gradients, and the lemmas are about the area vector. All right, now let's get back to the physics with armed with these results. All right, okay. So now let's calculate the AR of the, okay. So we know this is the by definition for a filamentary. Okay, we can for J, K, we can define this, but normally the most useful thing is the filamentary current I across, over a path DL. All right. So let's um, define our coordinates. Okay, this exactly the way we had done it for electrostatics. I'm going to do it, but except that it is for vector calculus. All right. So you can see that the same argument of multipole would work out, because this is 1 by R. Okay. So there also it was a scalar potential, but this was also 1 by the 1 by R. And hence the argument is going to be exactly similar. So if my origin is here, okay, and if I'm trying to calculate AR at a distant point, and this is the localized current, okay, and this is the angle alpha, okay, then so what this is something that we have already done, and hence I'll be very quick with it. So we have already seen we can write down 1 by R expand, okay, as in terms of Legendre polynomials, okay, which I did not use it very much, but we knew that we can do 1 by R. R is this, okay, R is this in terms of 1 by R, okay, this is a field point as a series. We can do a series expansion. Okay, please recall this. I have done this in great detail during electrostatics. It's exactly the same result. All right. So we'll do, so this of course in the variable cos alpha. All right. So I think you have just finished your midsem. I'm sure you would be remembering this. All right. So, and just to remind you that this was the Legendre polynomial definition. We would not require it in this chapter, I would not go into the higher order terms. I will stop with the dipole term. Okay, we have had already a lot of exposure to dipole term, sorry, quadrupole term in. So here I will not worry about the quadrupole term, but that's a useful thing later. All right. So now this substitute this expansion into my AR that I had written down there. That's straightforward. So then I'll write down AR. Of course, this is so mu naught I 4 pi I and summation R n plus 1 integral over the loop, okay, R prime n different powers Pn cos alpha dl prime. All right. So this is n going from 0 to infinity. Okay. So I can take that R is a constant. That is why I can take it out of, I have taken it out of integration. It's the same old idea. So now I can specially expand it to look at the first few terms. Okay. The first term is 1 by R integral over dl prime. The next term is 1 by R square R prime cos alpha. This is alpha. Okay. And the next thing is 1 by R cube and so on and so forth. I should have put plus dot dot dot. Okay. They are the first three terms in the expansion, in the multipole expansion of the vector potential. All right. So this is of course monopole. Okay. And this would be dipole and this will be quadrupole and so on and so forth. All right. So we know about this. All right. So what would be monopole? Monopole would be 0. How can you say that? This is a closed loop. So the total displacement going around the closed loop is 0. And we know that in a magnetic there is no magnetic monopole. All right. So it indeed comes out right from here. Okay. That if you integrate over a loop, then the total net displacement over a closed loop is 0. And hence monopole term in this expansion is always 0. All right. So so compare this with our VR term. Of course, there it was rho. I've taken here I out, and hence it is all over only the geometrical part. There, of course, it was rho. Okay, but exactly similar. So it was mu naught by 4 pi here, 1 by 4 pi epsilon naught. This was the monopole term. This was the dipole term, and quadrupole term, and octupole term, and so on and so on. So just compare with electrostatics. All right. So let's stay with this, and let me rewrite down that again. Okay. So because I am interested in the dipole term quite a bit. Okay. This is the full expansion. Of course, we can also use the quadrupole term. Quadrupole terms are used in magnetic field many applications, but we will stay with dipole. So monopole is 0, and let me state what I just said. The integral is just total displacement around a closed path, and hence is 0. I just said that. And it's also a reflection of absence of magnetic monopoles in nature. Okay, my AR, that is 0. All right. And then my dipole. Okay, so a dipole. So mu naught I by 4 pi. So that's the term. I've just repeated it here. All right. And so mu naught I. So there's the old trick. What is the trick? Vidit Narayan, can you please sit down somewhere? Why? Okay. So this cos alpha is, of course, I can write down in terms of, this is the old trick that we had done. All right. So now this is a constant vector. So the proof that I was doing so far for the lemma 4 was basically because to be able to use this result here. Okay. So r hat, okay, is a constant vector. Okay. So this is an integral over closed loop of constant vector dot r cross dl. Okay. So now I am invoking lemma 4. You remember lemma 4? That is C cross A is minus C. C is here r hat dot r dot dl. Okay. And hence This integral can be written as mu naught I by 4 pi a cross r. Because of minus, I have converted into a cross r here. All right, r hat. This is the constant vector. Okay, I invoke the lemma 4 here. So mu naught I, so 1 by r square. Now I take I and a, okay, together. This is the area vector A for any closed loop. All right. So that I now define as my, so my dipole A is mu naught by 4 pi. If I define IA to be my M is the magnetic dipole moment cross r hat by r square. Okay. So this is a potential, and that is why it goes as r square. All right. So I can write down this is the important result, that the vector potential of a magnetic dipole is mu naught by 4 pi m cross r by r square. Many people take it to be the starting definition. Okay. But I have spent more than half an hour trying to prove this. Okay. Through multiple expansion of the potential. Okay. So where, of course, we have defined I dA, okay, as I area vector. Okay. So compare this with the dipole. Okay. So this was P dot R by R square, V dipole. Okay. So here, instead of dot, of course, everything in magnetics is a cross product. So M cross R hat by R square. Okay. So similar, but in while doing magnetics, constantly you have to keep comparing it. What was the corresponding result in electrostatics? Okay. So, and sometimes you will actually use it in even in calculation. So you can easily generalize to volume current. I've done it for a linear current, but you can easily generalize to a volume current J, and that is I R cross. This is the generalized definition of the area vector. Okay, R cross dl. So this is lends itself to generalization to a volume current J also, of R cross J. I cannot take I out, so this is a J vector, and hence M can be defined for K, I, J, anything. All right, and once you have defined M, then a dipole, the vector potential is given by this. All right. Okay. All right, let me go to a logical point and then stop. We have time. So now let's look at the magnetic dipole field. Okay, so I've just defined that. So magnetic dipole moment is independent of origin. Okay, recall that P in electrostatics was independent of origin only when the total charge is zero. Okay, and hence, since there is no magnetic monopole, this is always true. Magnetic dipole moment is independent of origin. There is no conditionality because there is no monopole. All right. See the same picture, of course. Okay. So M, I just defined that. Now, magnetic field of a pure dipole moment placed at the origin. Let's calculate that. Since I now know the A, I can easily calculate field. Okay, we know del cross A. Okay, so curl of A is going to become field. So A dipole I know. I just wrote it down, and hence I can suppose I take the spherical coordinate system. Okay, then M cross R is M sine theta. Okay, M is, let's say, pointing in K direction. So K cross R, and that is 5. All right. So dipole, if I put my this thing in the at the origin pointing in K direction, then this will be this, right? This I can always generalize. Okay. So B dipole, if it is placed at the origin pointing in K direction, then this is this. Okay. This by simply by taking del cross A. Now for any point now I can calculate off axis. Okay. Remember, originally in the first slide, I had shown that we could calculate it only for the z-axis. Now I can, any point which should be far enough to be able to apply this localized current far enough, I should be able to use this. Okay. And does this remind you of something? This is exactly the same result for the electric dipole. Okay, 1 by 4 pi epsilon naught p by r cube, and so on and so forth. Okay, so so that's very pleasing. Okay, so I can also, exactly like in electric dipole, I can put it in the coordinate independent form, and that will be all right. So this is a just a simple algebra that you had done already in electrostatics. Okay. So this is 3 m dot r r and minus m. Okay. Now this is does not assume in which direction m is pointing, or this coordinate independent form. This assumes that the dipole is at the origin and is pointing in the k direction, k hat direction. This has no such assumption. So once I've written it this, I can write down it in any coordinate form. Okay. So there is a part which is r hat, and there is a part in which it's pointing in the m direction. All right. All right. So so now I just asked you to compare with electric dipole. It's exactly similar except for 1 by 4 pi epsilon naught here. All right. And this will be p, and this is similar. Okay, so it is not. So let's look at, so this is the, if we're pointing in this direction and that, okay. Now, a pure dipole would look like that. In fact, that still look like exactly like a, from a distance, by pure dipole, I mean that I am not worried, I am not going close to the loop. I'm very far away from the loop, such that the loop looks very small. And then, of course, the field lines look like exactly like E lines in a pure dipole in electrostatics. Okay, but if I go close, you remember this is fundamentally different. There is no plus monopole and minus monopole for a magnetic dipole, and hence if for a physical dipole it will look like this is a ring, this is a current ring. So, and these lines of force don't end anywhere, they're always continuous. We know divergence of B is 0. Okay, so they are very different if you look up close. Okay, for a electrostatic as compared to the electrostatic dipole. For a very distance, they will look the same because the formula is the same. Okay, but the magnetic lines of force, there is no source here. Okay, they are all continuous lines of force, and this is the current ring, and so they look physical dipole and a pure dipole. I hope you will remember that. We'll use this in the next few lectures. All right. Now let me take up a quick example, okay, of a gyromagnetic ratio. You must have already encountered this in your earlier school or even chemistry probably. Okay, so let's say there is a ring of mass charge, total charge Q and total charge mass M, and it is rotating with omega here. All right. So what is the current? Current would be Q 2 pi by omega. We know that this is the time of revolution. So I would be Q omega by 2 pi. And then we now know what is the magnetic dipole moment. Okay, so that is I know I, and pi r square. Okay, the area of the of this, and hence the magnetic dipole moment, of course, is pointing in the k direction. Okay, in the with the right hand rule. So this is half q omega r square. All right. Now, what is the from your last course? Of course, you know that the angular momentum L is m omega r square pointing in k direction. All right, and hence now I can write down that m, okay, is proportional to L, and what is that factor? That factor is called the gyromagnetic ratio. In this case, since it is m omega square r square k, and it turns out to be q by 2m. This capital M should be. Sorry. Okay, I'll change that to capital M because I'm using the small m for magnetic dipole moment. Okay, so this is capital M, q by 2m mass. All right, and there is a factor g. In this case, g is 1. It's called a g factor. Okay, that is called a g factor. So the magnetic dipole moment is proportional to L, and this proportionality constant depends on q by mass, q by charge. Okay, charge by mass ratio by 2m, and in classically G is equal to 1. This is called a G factor. So G factor is called G, and this whole thing is called the gyromagnetic ratio. All right. Important thing is that this is not dependent, and this ratio is not dependent on the radius or anything geometry. So suppose I have a spinning sphere, okay, then I can think of spinning sphere as a superposition of many such rings or donuts, okay, and they don't depend upon the radius. So this will still be the same, okay. So the gyromagnetic ratio of the spinning sphere will be the same, or anything that has is shape, a revolution of shape by which I can compose of such donuts, it will have the same gyromagnetic ratio, okay. So can I think of electron as a electron has a spin, you know that, right? Of course, classically you cannot think of it, but as a fundamental thing you can think of. Let's say electron is also a fundamental particle, and it has a charge which is spinning like that around that, okay. So what about that? So if an electron is thought of as a classically, then the gyromagnetic ratio should be the same. And now this is me, okay. This is the mass, okay. Then G and S. You know what is this S? Spinning, okay. This classically has no analog, so this spin vector is how much? Is h cross by 2. You know that from your earlier modern physics, okay. So h cross by 2. So, and what is the unit of h cross? This angular momentum. So you can think of it as an angular momentum, okay. So in fact h cross has the units of angular momentum. So all right. So classically, so you can now you can put this m square. In fact, it's called a Bohr magneton. Okay. So classically, G is equal to 1, as we saw, and then Dirac calculated through quantum mechanics. Okay, and calculated to be G is equal to 2, and got a Nobel Prize for it. Okay. So there are many people. There are many calculations. Okay, but that was not quite right. Okay, but it's quite close, but quite not right. But he got the Nobel Prize. Then quantum electrodynamics came, okay, from Feynman, okay, and that calculated G to be almost uh, 10 decimal places, correct? And this matches with experiment right up till here, okay. In fact, this is considered in terms of precision. There is absolutely no match in whole of physics, the match of theory and experiment, okay. And Feynman, Schwinger, and Tomonaga got the Nobel Prize for calculating this factor G. So this G factor is very important, okay. Even now, just in April, people are measuring the G factor for a particle called a muon, okay. And there is some deviation seen from what is predicted by theory in the 10th decimal place, and on that basis people are claiming that there is some more physics than what we call the standard model of the universe. All right, it is that important. So for every particle, a fundamental particle, we find out this G factor. Of course, this factor is a lot more important in experiments also. All right. So but just imagine a theory being able to predict up to 10 to the power minus 12 absolutely correct and measured experiment in both at Brookhaven National Laboratory in storage rings and also in Fermilab. This has been calculated to this kind of precision, and the theory and the experiment matches. But these are all because of quantum mechanics, which you are not dealing with here. But the idea that the gyromagnetic ratio is independent of the details of the geometry is an important idea, and you are going to use it in the next chapter. All right, I have a couple of minutes more. I'll look up all the after I finish. Okay, so a little bit of magnetic dipole and torque and force. Since some problems that is tomorrow there that involves this, Let me also take this up. All right. There are lots of chats, is it? Is there in the, okay, M has been used at 2 places. Okay, yeah. So people are making comments which are actually anticipating my lecture. All right. So let's quickly go through the torque part and the force part, which you in some sense know. But let me, why can't I take this off? Yeah, okay. All right. So motive is using the dipole approximation. In general, a force between two current distributions can be calculated through Bas-Savart law and Lorentz force law. Okay. And that would look like a little bit horribly complicated. Okay. We have to always do this. That is, of course, the fundamental Lorentz force. And where do I get B from? B from Biot-Savart law. So for two localized currents, then it can become, suppose it's localized current, okay, then it'll I1, I2, DL2. I've just applied this to linear current. And you can show that this is, if I have one, then the force, these are localized and well separated. There are two conditions that I put, localized and well separated. All right. Then you can show that the force is actually, suppose let's say F2. Of course, F1 would be Newton's third law. It will be exactly similar. You can simplify in terms of R. This was in terms of R2 and R1. And you can get rid of this cross products by expanding it and doing a little bit of vector algebra. And so this is R by R squared DL1 by DL1 dot DL2. Okay. But this is still it's a double integral. This is not in a very easy route. Okay. But if they're localized and well separated, one can do much better. Okay. Because we have now the dipole moment of one because of the other. Right. So that is the whole idea. So if the current configurations are well separated, one can take advantage of the dipole formulation. So, and consider each localized and well separated configuration to be superposition of dipoles. So I have done, suppose I have a big loop, okay, then I can always chop it up and think of many, many small dipoles over which the magnetic field is uniform, even if the magnetic field is not uniform, okay. But if I can always consider the localized current, okay, as a combination of small dipoles, and over the dipole area the magnetic field is roughly uniform, okay, and hence I can use my results of uniform magnetic field and small dipole moment, and hence it is actually, there is no loss of generality in doing that. All right. So that is the point that I wanted to make. So magnetic dipoles, forces and torques in uniform field. And if you calculate from a uniform field, then you can calculate from a non-uniform field. In a uniform field, the net force on a current loop is zero. That we know. Why? Because if it is uniform field, then I can take B out. If I take B out, then what I'm left with is integral over dl over a closed loop. And that, of course, displacement is zero. So there is no net force. Okay. So I know that. Now suppose but there could be a torque. Okay. And so I displace it, let's say suppose I take a small loop that I can take it. I have taken for convenience a rectangular loop. Okay. And as I said, that doesn't lose my generality because I always can consider a rectangular loop over a very small loop and displace it by theta. Okay. And let's say B, and my M is in this direction. Okay. So then I can see that this, if I see it from the force, the X point of view, then F is zero, but that can be torque because these horizontal forces are still there. They're equal and opposite. Okay. But they would give a torque. So force is zero, but there will be a torque. All right. So we can say that even in a non-uniform field, the torque is not zero. Sorry, uniform field. So the forces on the horizontal, this is what I call horizontal. Okay. So the net force on the loop is zero, but there is a torque. You can calculate the torque in this case, for example. So this is AF sine theta, right? This is the distance, okay, and this is A. So AF sine theta. And what is force? Force we know. Suppose this is B. Okay, B is this, and hence force is I small b, and I can put that into my torque, IAB sine theta, and torque is in the x direction, okay, and IAB I can write down as, oh, it's B is missing here, okay, MB sine theta, all right. So, and hence, this is good enough for me to be able to write down a more general result, okay, that is N is M cross B for uniform field, all right. So, how does that compare with electrostatics? Okay, the compare is, so P cross E is the same actually. All right, so neat. Okay, we've completely come with a different route, but they are exactly same or similar, let's say. Let's calculate a quick example in the next few minutes. Torque of, I can do this for any steady uniform field. I can leave it to as a task, but it will quickly go through this. Okay, that will also be M cross B. I did it for this for any arbitrary loop. Okay, I know this, and so I can calculate this. Let me go through this quickly. This is just algebra. Okay, R cross DF, I replace DF by this. Okay, and let me take up only R cross DL cross B. All right, then A cross B cross C, I can use that to expand this, and that's equal to 0. All right, I can still, please mute yourself. I can hear some background sound. Okay, so this is equal to 0, and I can rewrite this D of this quantity R cross B. All right, as I expand that, okay, as dr R cross B and R cross dr cross B. Okay, so I can, in my case, dr is dl, so I can rewrite this. So what I've done is I've taken dr as dl on this side, okay, minus, instead of minus I switched this B cross R, and then taken this on this side. So this is R cross dr cross B minus this. All right, just a little bit of this. Okay, so now R cross dr. So then by using this trick, I can, this is pure algebra. Okay, so I can write down this as 2R cross dl cross B, D of this whole thing, R cross B minus BR cross dl. All right, so my N, then Dn now, I can write down, okay, this was, so I can now plug this in into my Dn. Okay, so this is D of R cross B minus this. All right, so, and hence my the N vector, the total torque is just integration of that. All right, so that, of course, R cross B is 0. Okay, and what is this? This is R cross dl, and this is twice of A. You know, A, half R cross dl was A, so B to A, and there is a half here, and hence I can write down this as N is minus I B cross A, and I can write down M cross B. This is for any arbitrary loop. This is just pure algebra, but I had given you the feel for it by doing it for a square loop. Okay, but I just wanted to show you, you could have taken a circular loop, any shape, it doesn't matter. Okay, so this is M cross B, the same result that you obtain. Okay, so the last thing that I'll take up is net force in a current loop. Suppose there is a non-uniform magnetic field. A typical example, let's say coil, and there's a circular loop, and here the magnetic field is non-uniform, and there is a radial component. It's decreasing, right? So if I take it to be this loop, take it to be there, then there would be a net. If this would be the theta, then, and is the radius r, and the current is going like that, then there is a net attractive force downward. That is F cos theta. All right. So of course I know that so in a non-uniform field it is not zero, and so this I knew, I just shown you this is zero. But for a non-uniform field I can do that, and in this particular case, for example, I can see this if I be with this axis, if this theta, then 2 IRB cos theta. In tomorrow's tutorial, I have a problem first. I want you to calculate by using this formula. Okay, that's why I wanted to come here. All right, and so now for an infinitely small loop with a dipole moment m, I can always write down this as this. This can be proved rigorously, but take it from me. The rigorous proof requires a little bit of indices manipulation. I don't know whether you have done Levi-Civita tensor in 101 or not, but I will not, 102, but I will not go into it. So this the force because of m due to b. Okay, dipole moment can be given as this. Okay, and this will be can be proved rigorously, but I will not do it here. And so if this is force, I can always predict what is the energy, right? So that is, of course, minus m dot b. Now, is that looks familiar? In fact, exactly the same. Compare electrostatics. So in terms of P, F was, right, there was another formula, but if we write it in this form, it's exactly the same. Okay, and of course, U is also exactly the same, P dot E. All right. So suppose I take magnetic dipole interaction. Okay, this is my last slide. All right. Then so if I B dipole R, okay, we just found that. All right. So then I know this F. So I have to just take my dipole magnetic field and put my M there, right? So that's straightforward. So F, so the gradient of this field dot M2. So that is nothing but, so of course, 1 by r cube, but there's a gradient here, right? I'm using this formula. So in B due to this, I'm plugging into M2. All right. So that is straightforward. That was the whole aim of today's lecture. That is, I could take current combinations and then think of it in terms of dipole-dipole interaction, the force. All right. So here, of course, r is the distance between M1 and M2. Okay, I could have written down so without any complication, not from the origin. This is between M1 and M2. I can do this differentiation, and then if I do that, this r cube becomes r4. Okay, and then I can expand it in terms of M1 and M2. Obviously, you can see from here that it obeys Newton's third law. It is shorter range than Coulomb force, as you would expect. And if they point in the same direction as the separation, then the force is attractive. Okay, if you think of two magnets. Okay, and if they point opposite direction, then the force is repulsive. All right, you are going to use this or obtain this independently in the problems that I've given in the home assignment. All right, so at this point I'll stop recording and I can take questions for a few minutes. I'm over with my time though.